All right, everyone, in this video, we're going to talk about how to identify the substitution of a benzene ring, ortho, meta, para, by looking at the spectrum and analyzing that 6.5 to 8 region, the Aryl region. So as a friendly reminder, when you're looking at a benzene ring that is substituted, given where your substituent is, the adjacent position is going to be the ortho position. The position beyond that, 1,3 away, is the meta, and the position 1,4 away all the way across the benzene ring is the para position. Now, we're going to assume here that the substituents are different. So different substituents disubstituted, ortho, meta, para. Now, when you're looking at the Aryl region of 6.5 to 8, if you had a ortho substituted ring, there would be 4 signals corresponding to the protons of the ring, and none of them are singlets. So in the spectrum down here, you see 4 signals, and none of them are singlets. That would be indicative of an ortho substituted ring. Now you'll notice with the meta-substituted ring, when the substituents are 1,3 away, we're also going to see 4 signals in the Aryl region of 6.5 to 8, but there would be a singlet present, which is representative of the hydrogen between the 2 substituents. So on the spectrum, you'd see in that Aryl region 4 signals, but then there would be a singlet present. 4 signals and a singlet present indicates a meta-disubstituted ring. So ortho and meta both make 4 signals. Meta has the singlet, ortho has no singlet. With the ortho substituted ring, each of the signals will be split. Then a para-disubstituted ring with the substituents all the way across will only have 2 signals in the aromatic region. Both will be doublets, 2H doublet, 2H doublet. For example, here I've got a para-substituted ring. Notice in the Aryl region, I've only got 2 signals, 2H doublet, 2H doublet. So ortho, 4 signals, no singlet. Meta, 4 signals with a singlet in that Aryl region. And para is 2H doublet, 2H doublet. Now, let's say you see a scenario like this, where in that 6.5 to 8.0 region, your Aryl region, you see a signal that's kind of ugly like this. It kind of looks like a bonfire, and it integrates to 5H. That 5H bonfire, as I like to call it, would be what you'd expect if you had a mono-substituted benzene ring. A mono-substituted benzene ring. Now let's acknowledge that in theory, with a mono-substituted ring, you'd actually have 3 proton environments, but depending upon the identity of the substituent, those protons, which again, there's 3 distinctive sets, might be so similar in chemical shift that they blend up into one signal. Okay, that can happen, in which case they'd integrate that big old blob to 5H. If you see that 5H bonfire, it's a mono-substituted ring. So when we're looking at the Aryl region, we're kind of poised to identify if it's ortho, meta, para, or if it's a mono-substituted ring. And if in that region you don't see ortho, meta, para, or mono-substitution, there's some other number of signals with split patterns, then maybe you're looking at a tri-substituted ring with 3 substituents. And from there, you would just have to play around with how those 3 substituents would be oriented to get the correct number of signals and splitting pattern. Now, here's why we want to be able to identify ortho, meta, and para. And here we're going to look at an example of just given splitting data, how we could correspond that to structures. If you're just given data and you have to match it up to a structure, I would start with your most downfield shifting signals and work your way upfield, so highest ppm to begin with. Now, in that 6.5 to 8 region, you'd have your Aryl protons. Notice how there's only 2 signals there, 2H doublet, 2H doublet. That would be indicative of para-disubstitution. We could go right away and cross off answer choice A and E, as those are meta-disubstituted. Remember, those would have 4 signals in the aromatic range of 6.5 to 8, and there would be a singlet present. Okay, so I use that filtering factor of benzene substitution first and foremost. Then we go to the next signal, which is a 2H singlet appearing around 5.2. So 2H, that's a singlet with some good amount of de-shielding. What I'd do is go to each of the remaining answers and look for a 2H singlet. B has a 2H singlet. Looking at structure C, the 2H, notice is split into a quartet. Therefore, C does not correspond to the data. So now it's between B and D, and notice that D has a 2H singlet. So I can't really use that 2H singlet to distinguish them because while there would be a difference in chemical shift, that's a kind of a tough comparison to make. From there, I would look at the remaining 2 signals, 3H singlet and 3H singlet. Those will both be methyl groups that are not split. Now, in these types of questions, usually they're writing them to where you might get two structures with the same number of signals, the same splitting, but what's different would be the chemical shift patterns. Now remember, like looking at B here, methyl group adjacent to a pi system, methyl group adjacent to a pi system, proton on a carbon adjacent to a pi system would shift 1.5 to 2.5. Notice both of those methyl sets in the data are in that 1.5 to 2.5 region. That would be enough to say that B is our answer. Why D is not the answer is only one of those methyl groups is actually in that region of 1.5 to 2.5. The other methyl group you'll notice is bonded to the oxygen, and proton on a carbon bonded to oxygen would be 3 to 5. So the data would have to show one of those signals in the 3 to 5 range for D to be the answer. I can't stress this enough. There's subtleties in chemical shift that you need to know. Proton on a carbon adjacent to a pi system is 1.5 to 2.5. Proton on a carbon bonded to oxygen is 3 to 5. And remember, proton on a carbon bonded to nitrogen is 2 to 3. It's usually these regions that are contrasted in these types of questions. And to review kind of how I approach this, I looked at the aryl region first and foremost, because I had benzene rings in my answer choices. Some were meta, some were para. The 2H doublet indicated para. So I crossed off my metas. Then I went to the next most downfield signal, 2H singlet, and I tried to identify that in each of my structures. B and D both had a 2H singlet. The 2H in compound C would be split into a quartet, so the splitting pattern did not align with the data. From there, I looked at the next two signals, 3H singlet, CH3 singlet. Both are in the proton adjacent to a pi system range, and that aligned most closely with B. Methyl group adjacent to the benzene ring, methyl group adjacent to the C double bond O, so the chemical shifts could align. D would not align because one of the methyl groups would have to be in that 3 to 5 range as it's connected to the oxygen atom. Okay, so be prepared for a question type like this potentially. We read downfield to upfield, and you want to acknowledge these subtleties in chemical shift region because that likely will be the distinguishing factor that it will come down to as you problem solve.